Welcome to lesson 6.6, Properties of Trapezoids. So again, as we keep moving down the hierarchy of quadrilaterals, you want to keep in mind this idea that trapezoids include parallelograms, rectangles, rhombuses, and squares. So if it's true for a trapezoid, it's going to be true for those four other figures. So first thing we're going to look at, everyone's favorite, a proof. So it says, consider the figure at the right in which line DC is parallel to line AB. Fill in the missing justifications. So AB here, DC here are parallel based on this little arrow drawn in them. So what they gave us were our different conclusions. In this case, you won't see a given because they're just saying, consider this, fill in the missing justification, so they skip the given part. Kind of weird to do, but we'll go with it. So the first conclusion that they ended up giving us then was the measure angle 1 plus the measure angle 2 equals 180 degrees. So if we find angle 1 and 2 right here, they are a linear pair, and the linear pair theorem tells us the measure of the two angles equals 180 degrees. So our justification, the linear pair theorem. Then they told us measure of angle 2 is equal to the measure of angle 5. 2 being here, 5 being here. So if we think of AD here as our transversal, in between our two parallel lines, AB and DC, angle 5 and angle 2 are in corresponding parts. So the corresponding angle postulate tells us their measures are equal. And then in step 3, measure angle 1 plus the measure angle 5 is 180 degrees. They simply took steps 1 and 2 and substituted the measure of angle 5 in for the measure of angle 2. So that would be the substitution property of equality. If two things are equal, then we can substitute them for each other. And then last but not least, 1 and 5 are supplementary. So in this case, 1 and 5, that would just be the definition of supplementary angles, because the definition says that the measure of the two angles equal 180 degrees. So step 3 already gave us our reasoning. Step 4, we just had to rewrite that conclusion. Since they add to be 180, they are also supplementary, which comes from the definition of supplementary angles. Now, the reason that we're looking at that proof is because it's based on the trapezoid angle theorem. Trapezoid angle theorem states in a trapezoid, consecutive angles between a pair of parallel sides are supplementary. So 1 and 3 are consecutive angles next to each other in between these parallel lines. Same with 2 and 4. So angle 1 and 3 are supplementary, and also angle 2 and 4 are supplementary to each other. So the way we can use that is seen here in example 2. In the trapezoid below, TR is parallel to AP, and the measure of angle A is 60 degrees. Find the measure of as many other angles as we can. So our picture here, we have a 60. So I could figure out angle R right here by using my rule above, which states the measure of R plus the measure of A equals 180. They're supplementary. So 180 minus angle A being the 60 gives me the measure of angle R, which is 120 degrees. Then we'll take a look at the isosceles trapezoid symmetry theorem. So this is particular to just an isosceles trapezoid. And if we remember what an isosceles trapezoid is, it means that we have the two sides that are not the bases are congruent to each other, meaning then our base angle down here are also congruent. So in an isosceles trapezoid symmetry theorem, the perpendicular bisector of one base of an isosceles trapezoid is the perpendicular bisector of the other base and the symmetry line for that trapezoid. So the symmetry line is also the perpendicular bisector of the base on top and the base on bottom here. And if we'd fold it over that line, we would have our two symmetrical sides on top of each other. And then we have the isosceles trapezoid theorem, which just states in an isosceles trapezoid, the non-base sides are congruent. So that side and that side are congruent. So example 3 says WXYZ at the right is an isosceles trapezoid with the bases WZ and XY. So WZ and XY are my bases, so I know they're parallel. And then I know it's an isosceles trapezoid. So what I know right away is ZY here would be equal to WX here. So we could state that WX is 42 units. Then we can use the trapezoid angle theorem, which tells us if the measure of angle W was 45, we could figure out X by doing 180 minus the 45, which is W, giving us 135 degrees. So I know X is 135. So then we know Y is also 135 degrees because this is an isosceles trapezoid. X and Y angles are congruent. Same with W and Z. So we know that Z is also 45 degrees. And then our last theorem that we're looking at for this lesson is the rectangle symmetry theorem. And the rectangle symmetry theorem states the perpendicular bisectors of the sides of a rectangle are also the symmetry lines for that rectangle. So perpendicular bisector of our two sides here going sideways ends up being one of the symmetry lines, and the perpendicular bisector of the other two sides is also a symmetry line. And then you can see all the different congruent markings that we know based on these being bisectors and perpendiculars. So we end up with many small rectangles within our larger rectangle. But the big idea for this lesson goes back to this original statement that trapezoids underneath them in the hierarchy include parallelograms, rectangles, rhombuses, and squares. So we know that in a trapezoid, the consecutive angles between parallel sides are supplementary. That's also going to be true for our squares and rectangles. And you can do the same with our other theorems below. So as you go through the practice problems, I'd just highly recommend reading them carefully, taking your time to draw diagrams where need be, and making sure you're looking for parallel lines if you're looking for different angle relationships like we did in the proof here.